Hello, this is Andy from Engineers Academy, and in today's video we're going to be looking at the total energy demand, the electricity consumption and electricity generation primarily for the United Kingdom. We're going to begin by looking at some key definitions around energy data. We're then going to look at energy demand and final consumption for the UK. We're going to compare that with global energy demand, also known as primary consumption. And then we're going to look more specifically at electricity consumption and generation. Whilst considering electricity generation, we're going to look at some of the fluctuations that occur throughout the day, but also that occur throughout the months and seasons. Finally, we're going to discuss some of the future adaptations and solutions to some of the problems that we're going to be addressing throughout this video. So to begin, there's a few key terms that we need to understand when we discuss energy demand. The first term then is the total energy demand, which is also called primary energy consumption. Now the important point here is we're not just looking at the energy demand for producing electricity, we're looking at the total energy demand for things such as transport, electricity production, and also heating requirements for domestic premises and businesses. So we're looking at the consumption of all fuel types. And we'll also see that referred to as primary fuels, or the fuels at the start of the process. Now the important thing is when we look at energy demand or primary energy consumption, we're also including something called transformation losses. Now a transformation loss, as an example, is when we burn gas to produce electricity. The energy contained within the primary fuel or the gas is going to be more than the energy generated as electricity. So when we talk about energy demand or primary energy consumption, we're talking about the amount of energy that's actually locked inside the primary fuel, and it's impossible to recover all of that. There will always be losses, and we refer to those as transformation losses. Now, the next definition that we need to understand is energy consumption, which is also referred to as final energy consumption. Now, the difference here is that it excludes transformation losses. So using the example we used previously, the final energy consumption would be the amount of electricity that's being used, not the amount of energy that's locked inside the fuel. So when we look at energy consumption or final energy consumption, the value there is actually going to be less than the energy demand or the primary energy consumption, because it's the amount that's being used after those transformation losses. Now, energy consumption is measured at the point of use, so we measure the amount of energy being consumed by a premises as an example, or the amount of heat energy being produced for a home when we combust the gas, so it's measured at the point of use. Now, the final definition then that we need to understand is energy production or energy generation. Now, what we'll notice when we look at energy production data is that the amount of energy being produced is actually more than the amount of energy being consumed. And the reason for this is that we need to be able to generate enough energy to overcome some additional losses. Now, the best example of this is with electricity. If a power plant generates electricity, then the consumption of that electricity is going to occur elsewhere in the country. And during the transmission and distribution of that energy, there's going to be losses in overhead power cables as an example. So energy generation is measured at something called the point of common coupling. And this is where the power station actually feeds into the national grid. It's the point where the amount of energy they're producing is being metered for the purpose of calculating the amount of revenue being produced by that power station. So just to reiterate, the amount of energy being generated is measured at the point it's inputted into the national grid, but the energy consumption is being measured at the point of use. So that energy in effect has transferred through the transmission network, through the distribution network to the end user. And the amount of energy at the end is less than the amount of energy at the beginning due to these losses. So next then, let's look at some data for the UK energy demand and the final energy consumption. So here we see the demand for energy for the UK, and just to reiterate, this is energy demand, so therefore it's equivalent to the primary energy consumption. Now, the first thing we notice from this data is that a significant amount of our energy comes from natural gas, somewhere in the order of 40%. We also see that a significant amount of our energy demand comes from petroleum or liquid fuels. But we can also see that we've reduced our reliance on coal, and we're also meeting some of our energy demand through renewables and nuclear power. In terms of the amount of petrol or oil that we require, this is largely driven by the transport sector. And in terms of natural gas, some of this will be for electricity production and some will be for meeting the heating requirements of homes and businesses. We're still heavily reliant on gas both to produce electricity and to produce heat. Now, if we compare this data here for energy demand or primary energy consumption with the following data for final energy consumption, we notice a couple of things. First of all, as mentioned previously, our final energy consumption is lower than our demand. We see that our demand is somewhere in the order of 180 million tonnes of oil equivalent, whereas our consumption is around 130 million tonnes of oil equivalent. Now, as we mentioned previously, that difference will be as a result of those transformation losses when we convert primary fuel to final energy. A couple of other points to note: we see that transport, as we mentioned before, is heavily reliant on oil, and this is evident from the table underneath, where we can see of the total transport energy that's being consumed of 40.5 million tonnes of oil equivalent, 37.9 tonnes of oil equivalent are coming from oil. Another important point to note is that for domestic, we can see that a huge amount of gas, 25.7 million tonnes of oil equivalent, from a total energy consumption of 39.3 million tonnes of oil equivalent, is coming from gas. We can also see, as we would expect, that domestic consumes a large amount of electricity, as does industry, and as do our services. We mentioned before that a lot of the gas we consume is used for producing electricity, but it's also used for heating homes. Most homes will have a gas boiler for heating their water, but also for providing central heating. So just before we move on, I want to convert these million tonnes of oil equivalent to a different unit. And the unit I want to introduce here is called the terawatt hour. Now, the reason I want to introduce terawatt hours is because some of the later data that we're going to be looking at actually uses terawatt hours, particularly for electricity generation and consumption. And so we need to be able to see how one compares to the other. Now, we can see from our table that the total final energy consumption is actually 120.9 million tonnes of oil equivalent. The significant drop we see here, going from 2019 to 2020, was as a result of the pandemic on the amount of transportation that was occurring. So we see a significant drop here in transport, or the energy consumed by the transport sector, and that has a knock-on impact on the total energy consumption. So 120.9 million tonnes of oil equivalent is the same as 1,406 terawatt hours. The figure you see directly beneath that is for our total electricity consumption. So our total electricity consumption for the year 2020 was 24.1 millions of tonnes of oil equivalent, which equates to 280 terawatt hours. Now, once again, the important point to note is that this is final energy consumption. We would need to generate a surplus in order to overcome our transmission and distribution losses. Before we look in more detail at electricity production and consumption, let's briefly compare our energy demand with the global energy demand. So here we see the global primary energy consumption, which, as we already know, that's the same as the total energy demand, and we see this globally amounting to 160,000 terawatt hours. So we can see the global demand is over 100 times the demand of the UK, probably as we would expect. But when we look at this data in a little bit more detail, we notice a couple of other interesting trends. And I'm going to go to the interactive graph as we explain this. So here we see an interactive version of the same graph on the ourworldindata.org website. Now, a couple of things that we notice first of all. Using this interactive graph, we can actually see how much of that 160,000 terawatts came from each fuel source. So we can see that of that total primary energy consumption, 44,000 terawatt hours came from coal, 53,000 came from oil, and 38,000 came from gas. Now, the important point to get across here is that we saw previously that the UK was using very little coal for the production of energy, whereas that trend isn't replicated globally. We also saw that the UK was producing a significant amount of energy from renewables, and again that isn't a trend that we see here globally. What this demonstrates is that the UK is perhaps ahead of other countries in the uptake of renewable energy sources. It also demonstrates that not all countries are reducing their reliance on fossil fuels such as coal, and they're still heavily dependent on coal in order to produce energy. So what other evidence might support the fact that other countries are still using a lot of coal in the production of energy? Well, this table shows some additional interesting data, because what this shows by country is how much of their electricity is being generated from coal. Now we see that China still has a huge amount of their electricity being produced from the combustion of coal. And of all of the coal being used throughout the world, that amounts to 49.1% of all of the coal being used. We also see countries such as the United States and India using a huge amount of coal for the production of electricity. In actual fact, these 10 countries here accounts for around 85% of all of the coal being used globally. Now that's quite a staggering figure when we consider how little coal the UK is using in the production of energy. So it provides a useful point of comparison on how the UK generates energy when compared to other countries around the world. So next then, let's return to UK data, and now we're going to look specifically at electricity consumption and generation, rather than the consumption of primary fuels. So the graph shown here is the electricity consumption by sector. We can see that domestic consumes a lot of electricity, as does industry and commercial. But the important thing to note on this graph is that the total electricity consumption is around 280 terawatt hours for the year 2020, which corresponds with the data we saw previously. However, the data displayed previously was in millions of tons of oil equivalent, and we converted that to terawatt hours to give us a total electricity consumption of 280 terawatt hours. If we move on and look instead at electricity generation, what we'll notice is that the electricity generation is somewhat higher than 280 terawatt hours, perhaps somewhere in the order of 330 terawatt hours. Now that's because the electricity that's being generated is going to experience losses due to transmission and distribution before it reaches the end user. What we're looking at here is the amount of electricity that's being fed into the grid at the point of common coupling, whereas the previous graph looked at the amount of electricity being consumed at the point of use. So here we see electricity generation is somewhat higher than the electricity being consumed, and we can account for that difference due to the transmission and distribution losses. Another couple of important points to notice from this graph here is that the total amount of electricity being generated by renewables is significant when compared to the total amount of electricity generated. In actual fact, roughly a third of all of the electricity we generate comes from renewable energy sources. We also see a significant chunk of that energy coming from nuclear power plants. We can also see that a significant amount of that electricity being generated is coming from the combustion of fossil fuels, namely coal and gas. But we also know from earlier in this video that our reliance on coal, or the amount of coal that we're combusting, is very small, but we are still heavily reliant on the combustion of gas. Now, if we look at the UK's roadmap for the uptake of renewable energy, the plan is to have all of our electricity generation coming from renewable energy sources by the year 2035. By the year 2035, the intention is to decarbonise or eliminate the use of fossil fuels for the generation of electricity. So here we see at present around 120 terawatt hours of electricity being generated from renewables. The other important thing to look at is which renewable energy sources are contributing towards that. And here we see a breakdown of those renewable energy sources. Here in the UK, the primary providers of renewable energy are onshore wind, offshore wind and bioenergy. We do see some contribution from solar PV, hydro and waste, but the three main contributors are onshore wind, offshore wind and bioenergy. And these are trends that we would expect to see continue. Offshore wind in particular is an important asset for the UK because we're an island, and also wind speeds offshore tend to be higher and more consistent. So we would expect to see an increase in the uptake of offshore wind farms in the future. So the next thing to consider then is how our demand for electricity fluctuates. We've looked at the total amount of energy and the total amount of electricity more specifically being consumed in a 1-year period, or in the year 2020 as an example. But how throughout the year does our demand for that electricity vary? Well, here we're looking at data from the Gridwatch website. And Gridwatch collects data around our electricity demand and our electricity consumption. We're starting here with the yearly demand. Now, if we look at when our demand is highest, we can see that the time of year where demand is the highest are the winter months, November, December and January. Whereas the times of year when our demand is lowest are the summer months of June, July and August. Now, let's think for a moment why that might be. Obviously, during the winter, the days are shorter, so we have a higher requirement for lighting. There will also still be a lot of people in the UK who have electric heaters. And another factor might be that people go out more in the summer, so they're less likely to be at home where they would be consuming electricity by watching televisions or playing on computers as an example. Now, working backwards then, if we look at monthly demand, what we see from a day-to-day basis is that the energy demand changes. So we have 5 days with high demand, and then we have 2 days with a lower demand, 5 days with high demand, 2 days with lower demand. Now, as I'm sure you can appreciate, what this represents is the working days, Monday through to Friday, when the consumption of energy by businesses and industry is increased, and at the weekend when people are at home, demand tends to reduce. So we see these kinds of fluctuations. The important point to note here is that we still need to be able to ensure that we can provide the electricity as and when it's required. Let's break these increments down a little bit further then. Here we have the demand during the week. Now, as we said before, we can see that the demand on Saturday and Sunday is slightly lower than Monday, Tuesday, Wednesday, Thursday and Friday. But what we also see is throughout the days, the energy demand fluctuates. So we have when people are sleeping, and then they get up to go to work and we have the working day, and then when they get home, we see another spike in the use of energy. And this trend continues throughout the week. We see a similar trend at the weekends where the demand in the morning is perhaps somewhat lower than in the afternoon and evening. Now, if we look at an even smaller section of data, then we can confirm what we've just stated there. This is looking at daily demand, and we can see that through the night, from midnight to around 6 in the morning, demand is low. At 6 in the morning, demand begins to increase until we get to around 9 o'clock, and then throughout the working day, between 9 and 5, the demand remains fairly constant until people return from home and we see an increase between 6 and 8 before demand begins to drop off again as people go back to bed. Now, this is only part of the picture, because if we were to look on even smaller increments, maybe hourly or by minute or even instantaneous energy demand, we need to be able to ensure that we can provide the energy as and when it's required. So this brings us on to the second column of graphs, which is also quite interesting because what we see here is how that electricity is being provided by different sources. Now, if we look at the first line here at the top, the blue line, this is the energy being provided by wind, and we have no control over the amount of energy that's being provided by the wind. However, we need to be able to meet those increased demands from 6 o'clock to 9 o'clock and throughout the working day. And what we see is that that's actually being provided by our combined cycle gas turbines. So when demand increases, more gas is consumed in order to meet that demand. Then as that demand decreases, the amount of gas once again is reduced and we're no longer producing as much electricity by the combustion of gas. If we look at our second graph then, where we have these definite spikes at around 5 p.m. each day, how is that demand being met? Well, it's being met in part by our combined cycle gas turbines, but when demand is particularly high, we have another alternative. Over here on the right-hand side, we have pumped hydroelectric storage plants. Now, pumped hydroelectric storage is a means of storing electrical energy in the form of gravitational potential energy. So when demand's low, we pump water into an upper reservoir, and then when demand increases, we release that water from the upper reservoir, and as it travels down to the lower reservoir, it will pass through a turbine and create electricity. So if we were to expand this out, we would see that where our peak demands are, at say 5 p.m, the way that that demand is met each day is by these corresponding spikes from pumped hydroelectric storage. And we could follow this trend throughout the various different graphs here. The important point is our renewables provide a baseline. Our combined cycle gas turbine is used to meet demand as demand increases. And when we have peaks in demand, such as at 5 p.m. on a weekday, we can release energy from our pumped hydroelectric storage plants in order to meet that instantaneous demand. The eventual goal then is to rely solely on our renewable energy sources such as wind and storage technologies such as pumped hydroelectric storage, and other energy storage methods are available and currently being developed. So the last thing that we need to look at then is any future adaptations and solutions to some of the problems that we've discussed throughout this video. Now, some of the solutions that we know are currently being incentivised by the UK government are things such as the introduction of electric vehicles to replace petrol-powered vehicles. Now, the benefits of doing so is to reduce petrol or oil consumption, and as we saw earlier, a considerable amount of liquid fuels are actually consumed by our transport sector. We're also going to see an increase in the uptake of air source and ground source heat pumps. Now, air source and ground source heat pumps can be used by businesses or also by domestic premises to meet their heating requirements and also their hot water requirements. Again, the benefit to this is that we would see a reduction in the amount of gas that we're consuming as a nation. So if we can reduce our oil consumption and our gas consumption, the knock-on benefit of that is that we'll also be producing less CO2, which is one of the contributing gases to the greenhouse effect. We've already mentioned that the UK government's aim is to decarbonise the power sector by 2035, and in doing so, we're going to reduce our fossil fuel consumption, but we're also going to reduce those CO2 emissions. Another area for development is improving electricity storage technologies. As mentioned previously, if we are going to decarbonise the power sector, then we need energy storage technologies to meet these instantaneous demands at various points throughout the day. We saw how this can be achieved using pumped hydroelectric storage, but the initial setup costs for that type of arrangement are very expensive, and it also has various ecological and environmental impacts. So any additional electrical storage technologies that are more environmentally friendly, but also economically viable, are worthy of further exploration. So finally then, we mentioned the importance of increasing the uptake of renewable energy sources, and one of the important aspects of that is the cost associated with developing a renewable energy technology. What we're looking at here on the left-hand side is something called the levelised cost of electricity for the year 2025 and the same levelised cost of electricity for 2035. Now, levelised cost of electricity is a measure of the cost to produce a given amount of electricity using a specific energy source. So really what it amounts to is a direct comparison between the cost of various different energy technologies. As it's the specific cost to produce a specific amount of electricity, namely 1 megawatt hour, we get a direct comparison of the costs for each of these technologies. Now let's begin by looking at the graphs on the left-hand side. We can see that offshore wind is slightly more expensive than onshore wind, and we can see that that difference in cost is largely due to these costs here, which are construction costs, and these costs here, which are operating and maintenance costs. So as we would expect, it's more expensive to build and maintain an offshore wind farm. The costs for onshore wind and large-scale solar are relatively comparable, £46 per megawatt hour when compared to £44 per megawatt hour. The difference being there are variable operation and maintenance costs for onshore wind. What is important though is in the year 2025, it's been projected that it's going to be more expensive to commission and build a combined cycle gas turbine plant or a combined cycle gas turbine plant with carbon storage or post-combustion. And we see that that difference is quite significant. To build an offshore wind farm is going to cost £57 per megawatt hour of production, whereas to build a combined cycle gas turbine is going to be £85, both with and without carbon storage and post-combustion. But we see some new costs introduced here. First of all, we see a fuel cost. It costs money to purchase the gas. So purchasing the gas costs money, which increases the price per megawatt hour of electricity being produced. We also see another category introduced here, which is the carbon cost. So previously we had the cost of the fuel, now we have the carbon cost. Well, the carbon cost actually comes from UK government taxes in the form of carbon price support as part of the climate change levy. So another way that the UK government is de-incentivising the combustion of gas to produce electricity is to include a tax on the amount of combustible gas or other fossil fuels that are being consumed, and this is directly impacting on electricity generators. So moving on to the year 2035, we see the cost of offshore wind, onshore wind and large-scale solar decreasing as the technologies improve and infrastructure improves. We also see that the cost of the combined cycle gas turbine plant with the carbon storage and post-combustion is slightly lower than in the year 2025. Now this is largely due to the fact, as you can see, is because the carbon taxes are significantly reduced where carbon storage is being employed. Now, although this graph isn't to scale when compared to the left-hand side, we do notice that the combined cycle gas turbine without storage and post-combustion is significantly more expensive than previously. We see an increase from £85 to £115, and that increase is largely coming from the increased taxes that are being applied by the government. So we can see that the government is de-incentivising the use of gas for fuel unless carbon storage and post-combustion is also being employed. But once again, this reinforces the fact that the government is aiming to decarbonise the power sector by the year 2025. And the way it's doing that is, first of all, by de-incentivising the combined cycle gas turbines, unless that's being used in combination with carbon storage technologies. Now, carbon storage is just a way of capturing CO2 and storing it under the ground. And what that means is it isn't being released into the atmosphere and causing damage. It may also be the case that that carbon dioxide can be used for other things. So just to summarise then, in this video we've looked at different ways of quantifying energy data, both in terms of primary fuels and electricity. We've looked at the UK's demand for primary fuels and we've compared that with global data to see how the UK's energy mix differs from other countries around the world. We've then looked at the UK's electricity consumption and generation, both on an annual basis, but also throughout the year, throughout the month, and throughout the days of the week. In doing so, we've identified various different fluctuations which occur, or various different peaks, which actually occur at predictable times during the day, week, and month. Then finally, we've summarised some of the potential future adaptations and solutions that could be employed in order to overcome some of the challenges that we've seen throughout this video. So I hope you found this video useful, and thanks for listening.